Welcome to the second day of CORDS COMAT 2019. This morning, actually, I have the privilege of introducing a very well-known figure in AI, that is Professor Subbarao Kambhampati, and he's generally known as Rao. And Professor Kambhampati is a professor of computer science at Arizona State University. He received his BTech from IIT Madras and his master's and PhD from University of Maryland, College Park. And he studies fundamental problems in planning and decision making, motivated in particular by the challenges of human-aware AI systems. Professor Kambhampati is a fellow of AAAI and also AAAS, and he was an NSF Young Investigator. He received multiple teaching awards, including a university last lecture recognition. And Professor Kambhampati served as the president of AAAI. I think most of you may know him because of that, and is also as a trustee of IJCAI. And he was a program chair for several conferences, very well-known conferences. For example, IJCAI 2016, ICAPS 2013, AAAI 2005, and AIPS 2000. He serves on the board of directors of Partnership on AI, and Professor Kambhampati's research, as well as his views on the progress and social impact of AI, have been featured in multiple national, international media outlets. So we are very happy to have him here. Please welcome Professor Kambhampati. Thank you.
Can you hear me? Can you hear me? Okay. Yeah. Okay. Thank you. Good morning, all. So I am going to be talking about this topic, challenges of human-aware AI systems. First of all, thanks for waking up and showing up early in the morning, established by Kolkata standards. So one thing that I wanted to start with is, as I was walking around, I was here yesterday, and as I was walking around the hallways, there was this burning question about this conference, whether CORDS COMAT is really a conference on data science or databases, and whether or not it is fully representing both of those things. Actually, as I guess an early bird present, I can answer this question for you. It's neither. It's basically another conference on artificial intelligence, as far as I can tell. What other conferences can actually get their registrations closed because of too much interest these days. So really, it is an AI conference in multiple ways, and that's great for me because to me, that's a high compliment to say for a conference. I have been essentially working in AI more or less longer than pretty much everybody other than maybe Ray Mooney here. And this is my 1983 bachelor's thesis on speech recognition, clearly before the laser printers were invented, so I had to draw my beautiful speech recognition architecture with hand. So one thing that's different between then and now is my time when I was interested in AI, people used to feel sorry for me. How come you're not working on more exciting areas such as databases or at least software engineering? Why are you working in AI? Clearly, things have changed now. Basically, you almost have to explain yourself if you're not working in AI and you happen to be in computer science as to why are you even wasting your time. A lot of people actually think that computer science department should be more than half just AI people. That's where we have come to. And of course, there has also been significant public hype around AI. So AI has been likened to the new electricity. It's been said to be bigger than both fire and electricity. AI has been likened to God itself, or himself, or herself, or whatever the heck you want to believe in God. And of course, every possible consumer product has to have AI in it, otherwise it's a totally lost cause. So apparently even toothbrushes now have AI in them, and they will use smart, intelligent techniques to brush your teeth. I'm really worried about those. There's also been the other side of the coin. There's been significant worries about AI. AI is seen as a bigger threat than North Korea, and that AI will start the third world war. I don't know exactly where Elon Musk gets his time between all the delayed Tesla deadlines, but somehow whenever he gets time, he will say something about how the AI is going to end the world. Stephen Hawking, before he passed away, he did feel that AI could be the worst event in the history of civilization, which is kind of nice because all my life, during my graduate school years, all I would hear is physicists saying AI is not possible, why are you wasting your time? So physicists cannot make up their mind as to whether AI is not possible or whether it's going to kill us all. And then, of course, Alan always is, can be counted on to say balanced things such as AI is highly likely to destroy humans before this being a worst event in the civilization. So I don't know how many of you know this guy, Oscar Wilde. And he said something about America. Oscar Wilde is a Brit, and he didn't particularly care for America, I guess. He didn't actually, he's a misanthrope. He didn't care about human race to begin with. And so what he said was, America is the only country that went from barbarism to decadence without civilization in between. I'm always very worried about even repeating this quote in US, given our current administration and my color of the skin. But here, of course, you all look like me, except race, so I can say this without too much worry. So when I look at this, I think, is AI the only technology that went from disappointment all my life to deadly to the other end without ever touching beneficial nature in between? Clearly, that's not the case. Obviously, it's a whole bunch of hype around viewing what AI is doing. But as was pointed out, I served as the AAAI president the last 2 years, and since most of the hype happened during the last 2 years, and since there is no such thing as bad publicity, because all publicity is good publicity, I take credit for this modestly, and I think that I have made AI great again. So that's the state of AI. Given that this is a data science conference, before I go into talking about human-aware AI challenges, I thought we should establish some sort of a common ground, because data science people think they're doing AI, but the first question is, if you're doing AI, what data are you using? That's it, as if the most important question about AI is what data you're using. So I want us to broaden our outlook a little bit. And so let's start with the intelligences. There are many kinds of intelligences. If you think of a human baby, and you see them grow, so they start with perceptual and manipulation intelligence. They look at the world, they look at their mothers and fathers, and then they try to put everything into their mouths. Then they start showing emotional intelligence, smile at their mothers and fathers. Babies who scowl at their mothers and fathers don't actually live on too long because they don't get any care. And then they start having social and communicative intelligence, including language, and having theory of mind. What are other people thinking, approximately. And then finally, if you are rich enough, you send them to schools, and then they start getting this cognitive and reasoning intelligence, the ability to essentially the kinds of things that get tested on your SAT exams or your JEE exams and so on. Now, of course, this last one is more declarative and consciously accessible. Now, keep this in mind, and the last time around, AI had a huge, big hype, was around 80s when there was expert systems craze. Then there was 90s when there was this whole Kasparov was dethroned by Deep Blue, which was a reasoning system. And then more recently, of course, we started making big progress in perceptual tasks, the ability to see the world, the ability to hear the world, and maybe a little bit about how to manipulate the world, physical world. Now, the interesting thing about that is the direction in which we have made progress in AI has been exactly almost the opposite of the way human babies seem to show intelligent behavior. So instead of showing perception first, then emotional, and social, and then cognitive, we went directly from cognitive, and we just about got to perception now, okay? And I think it's a very useful thing to keep in mind to avoid a lot of misunderstandings about the overall scope of AI and what your place is in that enterprise. So I kind of tend to think that this particular realization that AI went in the different direction, opposite direction from the way human babies show show intelligent behavior, explains a lot of things. For example, why did AI develop this way? The first things we did was to program computers with intelligent behavior. We could only program with what we already know. If we have conscious theories of a task, then we can program a computer. There are certain things for which we have consciously accessible theories, and that's where the reasoning, how to play chess, how to play Sudoku, these are things we could write the computer to program a computer and let, for example, it do search through multiple configurations and so on. Vision, speech, we had no idea. In fact, it was like a futile attempt that vision and speech as areas tried to have major theories about how human vision is done, how speech is done. It's all become a footnote now because essentially we are not consciously aware of how we do, how we see the world or how we hear the world. And certainly also certain kinds of manipulation, physical manipulation. In these cases, we just had to do what babies had to do. And I don't know if you have noticed, babies mostly spend their time being cute and doing nothing for long years at a stretch. Some babies are overgrown, 20 years, they haven't left your home, but still they're essentially what they're doing is they're observing the world and trying to learn from their observations. So there's nobody telling them how to do the task. Now, the interesting thing is there are some tasks for which we cannot actually tell them how to do it, such as vision and speech, and for that we had to wait for essentially database techniques like learning. It's important to understand that because if you do not realize that, then this is another point that I want you to think in terms of. There's this guy called Polanyi. He's an amateur philosopher and polymath, and he essentially has, the Polanyi's paradox is basically he's saying that we know a lot more about the world we live in than we can explicitly express in language, for example, because declarative typically tends to mean explicitly expressed in language. So he was worried about the fact that much of science and technology seems to be focusing on things for which we have explicit models that are declaratively accessible to us, and that he wanted us to also think about this tacit dimension. In fact, there's this book that he has written called The Tacit Dimension, which is trying to say that we need to understand how we do these tacit tasks that we seem to do without having access explicitly to how we do this. This has been called the Polanyi's paradox. The interesting thing about this is, if you haven't heard about this before, this is the first time you heard about this, now I would say that not only was there a Polanyi's paradox for the longest stretch for AI, we now are in the phase of revenge of Polanyi. In some sense, the AI pendulum has swung from essentially, let's try to work on only tasks for which we have explicit models, to what do you mean models? We should just essentially, whatever it is that you want to do, you just want data. From the data, we'll try to figure out how to make decisions. Sometimes that might be the only possible way you can go around doing things, but sometimes there are essentially humans in the loop can provide you information about what's the rules for the game, rules for the task. For example, a crazy extent to this, which this has been carried on, is things like somebody trying to solve Sudoku program, the puzzle, by essentially deep learning. So you just have a billion examples of Sudoku puzzles and their correct configurations, and then try to learn from that. That's an extremely silly thing to do because you can essentially write 3 lines in declarative fashion as to what is essentially a Sudoku puzzle supposed to satisfy. Okay, so one of the hallmarks of the human intelligence is actually the seamless interplay between tacit and explicit knowledge. We see a face, and without reasoning, we'll be able to realize that this face seems to be a scowling expression. But at the same time, we also have explicit models of the tasks at hand, and we combine both of them in doing our reasoning. And so it's important to keep that in mind so that you don't just always think in terms of what is it that I can do from data. In particular, actually, if you join, for example, a company, if an AI agent joins a company, and if the company says, here is a doctrine. Here is our manual of behavior that you're supposed to do in this company. This is the manual of operations. An AI agent will say, no, that's something that you wrote. I don't want any knowledge. I can essentially try to observe the company in action for a gazillion years, and then figure out what's the right way to behave there. That's unnecessary when you should be able to take actually somebody providing knowledge to you. So there is the serenity prayer in Christianity, which says, God grant me the serenity to accept the things I cannot change, courage to change the things I can, and the wisdom to know the difference. And recently I made a version of that for the robots, the robot serenity prayer, which basically says, human, grant me the serenity to accept the things I cannot learn easily. So just basically provide me the knowledge, data to learn things that I can, and wisdom to know the difference. Please don't go around trying to solve Sudoku by deep learning. It's kind of a silly thing to do. Okay, so keep that in mind. And having said that, there's a lot of hype about AI and a lot of press coverage about AI. And the kind of stories that I'm particularly interested in about AI are the kinds of things shown here. This is a nice breaking news about AI systems helping old ladies crossing the street, playing with kids, cooking food, and hanging around with other humans sans drama. No drama, nothing, just basically getting along with others, just like we do. Now, this looks like legitimate news, and you are surprised probably as to how you missed this in the midst of all the AlphaGo news and so on the CNN. It's because it's fake news. I just made it up. It turns out that you can make fake news, ask our president. So it turns out that, so the question really is, why is it fake news? Why aren't we seeing stories about this kind of a thing in day-to-day press, as against AI is about to kill us all? AI is going to lie, cheat, whatever, all sorts of random things. Why is it that we don't talk about AI interacting with humans in the loop? So it turns out that AI had a long-standing, curious ambivalence to humans. Our systems, AI systems, seem happiest either far away from humans. For example, Spirit and Rover hanging around on Mars, where unless you believe in National Enquirer-style conspiracy theories, there are no humans, and are in very adversarial stances with humans, such as creaming humans in chess, creaming humans in Go, creaming humans in poker. So is it any surprise that when you talk about AI to a normal person on the road and say, we are here to help humanity, they say, oh, please leave us alone? Because mostly we seem to be working on the adversarial problems with humans in the loop. It's almost, John Lennon, one of the famous singers, of course, most of you know, especially if you're a little older, has said this: you want to help humanity, it's the people that you just can't stand. And I sometimes think AI has this problem too. AI wants to help humans, but it's just the people that get into the way. So one of the reasons actually AI systems and the interaction between the AI systems and the humans hasn't received much of a research support over years is partly because there was this worry that working with humans, letting humans being in the loop, might be a form of cheating, because humans will solve the problem and the machine isn't going to do anything. After all, the original mechanical Turk, not the one that Amazon makes you, pay for, but the original mechanical Turk was an actual contraption where there was a little Turkish man, Turk, sitting inside providing the intelligence for this entity. Now, of course, it's that sort of prestidigitation is alive and well. There is Sophia the robot, which is basically nonsensical as far as AI is concerned. Any of you who read Sophia articles and think, wow, this is great AI, please, stop yourself from doing that. And then remember recently, last week or 2 weeks back, in Russia, there was this amazing robot that was going around doing all sorts of beautiful things, and they found, when they removed the robot's cap, that there was a nice human being inside. Okay, so humans in the loop have basically given us, there is this worry that maybe humans in the loop are there to cheat rather than let the system do everything. But one of the things that I looked at in last February, as the president of AAAI, I got the bully pulpit to talk about an address to the community, and so I talked about the challenges about human-aware AI systems, where Basically, I looked at this question, why isn't human-aware AI all over the place already? Why should we be pursuing it? And what are some of the specific research challenges? And one of the things I pointed out for there, and then I'll point out here again, is that essentially working with humans in the loop increases the ambitiousness of the AI enterprise. It doesn't make it smaller, it makes it harder, actually. And researchers are masochists. Researchers basically want problems to be harder rather than just much simpler. And so, in fact, if you, in this spectrum of intelligences, emotional and social intelligence never really received much of an interest from AI community. It's sort of like the Rodney Dangerfield of AI. It's like they do, intelligence is like basically they never get much of a interest from the community, and it turns out that if you have to work, if AI systems have to work with humans in the loop, they need the social and emotional intelligence in particular, okay? So, and another way of thinking about this is actually human-aware AI expands the reach and scope of AI enterprise because, you know, there is this evolutionary theory that says that we needed the brains we have, the bigger brains we have compared to our evolutionary siblings, not to run away from the tigers of Sundarbans or lions of Savannah, but to deal with each other. We are constantly modeling each other's mental states and strategizing with or against each other. So there is this whole argument that, in fact, the reason for the brain size increase was this requirement of social intelligence. I don't know how many of you know the Sally-Ann test. Sally-Ann test is this really nice small psychological test that they give, where Sally, for example, the girl in red, comes in and puts her ball in the yellow box, and she goes out of the room. Then Anne comes in and puts that ball from the yellow box into this gray box. And now the question is, when Sally comes into the room, where would Sally look for the ball? Those of you who are thinking this is JEE level question, you are in trouble. The interesting part about this is that kids below 4 years of age have trouble answering this because they have realized that Anne has put the ball in the gray box. Since they know it, everybody else should know it. And so they assume that Sally also knows it. And beyond 3, 4, 5, and so on, they say, why are you wasting our time with these kind of silly questions? Because after all, Sally won't know where, Sally would still think that the ball is in the yellow box. The interesting point here essentially is there is this notion of theory of mind, the ability to understand that your beliefs are different from other people's beliefs. As an AI person, I was ecstatic when my son told the first lie. You know, I understand that Gandhi will be turning in his grave, but the point is the ability to tell a lie shows that you understand that what you know may not be known to another agent. And that's a theory of mind. And, you know, you can talk about is lying good or bad. That's a whole entire different issue. Integrity is ability to know, knowing that you can cheat and choosing not to, as against being brain dead and not even knowing that you can cheat. Okay? So it is important that the social theory of mind essentially increases the number of problems that AI systems have to deal with, because now they have to have a model of the humans that they're interacting with. Now, human-aware AI systems have always been around in areas such as intelligent tutoring systems and social robotics. You know, these little robots that play with kids are intelligent tutoring systems, of course. Who else are you trying to teach if you don't care about the human's mental model? But it's beyond that. It's even though, while those areas used to think about these questions, it's actually much bigger than that. All AI systems have to understand how to interact with humans. Otherwise, why exactly are we developing these systems that would not actually care about interacting with us? Okay? So these are not the only ones. The intelligent tutoring systems and social robotics are not the only ones. Anywhere a system is providing assistance or working with humans, it has to have the ability to provide, you know, have a model of the humans and use that to collaborate with them or to help them. And if, in fact, it's AI, if all of computer science is becoming AI, there is this area in computer science called human-computer interaction. That will actually become human-AI interaction, because much of interesting connections that you want the computer programs to do would essentially have to show intelligent behavior. So this is sort of the long-winded reason as to why we should be interested in looking at these kinds of problems. Back in 2016, when I ran IJCAI, actually we had a special theme for the conference as Human Aware AI with the tagline being, why intentionally design a dystopian future and spend time being paranoid about it. You'd rather want to work with, develop technology that works with humans. And then, of course, AAAI has special tracks on human-AI interaction these days. And then the Partnership for AI has 7 pillars, thematic pillars around which it organizes its work. And one of them is collaborations between people and AI systems. And so those are all the reasons why you should be interested in human-aware AI systems. In terms of what has to change if you are suddenly actually thinking of humans as a part of the problem that you're trying to solve, is if you look at a intro to AI, intelligent agent architecture, this is the kind of thing that you will see in the first intro classes. And the moment you introduce humans, originally in this kind of architecture, humans are there as part of the environment. They are just part of the inanimate environment. They are obstacles that you want to get around as against actually model them and model their intentions and beliefs. Once you actually consider human mental model, then every part of this intelligent agent architecture will wind up changing. So it's not a single piece gets left alone. And that's the important thing to understand, that in fact it's a pretty big change to have human AI interaction. And so in fact there's a tech report on some of the challenges on human-robot cognitive teaming that's available out there that basically writes down some of these challenges. What I want to do in this talk is to look at specific challenges that come in the context of planning and decision making, because that's sort of closer to my heart. So when you have an AI agent trying to make plans, but humans are also in the loop, either as observers or as collaborators, what are the kinds of research challenges that you have to handle? And it turns out that, and I'll go into more details in a minute, but the two big things wind up being modeling and managing humans' mental state, and also modeling and managing humans' model of yourself. So it's like a two-level interaction. One, the robot needs to understand what humans' capabilities are, and it also needs to understand what human thinks its capabilities are. That is actually managing humans' understanding of your capabilities winds up being very important in showing behavior that is explicable and in providing explanations to the humans, as I will get through the talk to become clear to you. So the kinds of use cases that we have done in our research in working on these kinds of problems are twofold. One is the human-robot interaction, which is shown as one of the one on the left-hand side, where there is like a collaborative problem solving with either a human being an observer or an actual partner in the problem. And the other side, you have essentially a system, a software system with the human in the loop, where you're trying to help the human's decision making with the AI system, sort of letting the human be in the steering position while still offering appropriate help, as against taking the steering wheel from them. Those are our cases. So in terms of getting these models, I mentioned that the AI agent needs to have a model of the human's capabilities as well as human's model of its capabilities, both of which are approximations that it needs to keep track of and use them in coming up with its own plans and decisions. So starting from like a single agent, and a single agent essentially has, let's say a robot has a model of the world, and then it uses that to essentially reach some goals, such as start from a state. It does the kind of actions that it can do to reach a goal state, and then it will then execute those. That's essentially planning problem. Now, the moment you have a human in the loop, essentially the human might have his or her own actions that they are capable of doing, and the robot needs to be able to keep track of that. The fact that I can do these pieces, you can do these pieces, so I want to take that into account in trying to provide appropriate help to you and figuring out what parts of tasks I should take over and what parts of tasks that I should let the humans provide support for the humans. So this will allow, that is, reasoning with MH, which basically requires the robot to have this MHR, which is robot's own approximation of humans' capabilities. It has to basically use that to essentially reason about how to provide collaboration. Now, the other aspect is the humans too in the loop have some default expectations of what the AI system is capable of. Okay, and that would be actually MRH, and the robot essentially needs to have an approximation of that too. Because that's what I was saying. If you do not know what people think are your capabilities, then you cannot provide explicable behavior, the behavior that is comprehensible to the humans in the loop. Okay, and also it turns out that is the model that winds up being very helpful in providing explanations. So it turns out that it's these two approximations that I will talk about mostly. There are two aspects to these approximations. One, of course, is where are they coming from, the learning part. The other is how are you using them, which is the inference part. Coming from the planning side, I will spend more time on the inference part, but I will describe some of the work that we do in essentially learning those models, and also point out that in some cases, essentially, these approximations might be available as the starting points when, for example, the human and the robot would have the same model they start from, and then they diverge over because the robot actually gets more knowledge during its execution. Okay, so in some sense, it's essentially this tale of these two approximations that you have to handle, the approximation models that you have to handle in providing appropriate help to humans in the loop. And in looking at the first one, which is basically getting a sense of humans. When I say models, by the way, I mean the actions, the goals, and the initial beliefs of either the human or the robot. So that's what I mean by model. And so teaming, of course, requires modeling the human. This is sort of not new. I mentioned this in terms of the Salian test aspect. And so, in fact, this requires intention recognition, recognizing the intentions of the humans in the loop, and providing a projection of your own intentions. Where are you going next? So if you are alone, you just can do your work. You don't have to say where you're going, but you have others in the loop. You need to provide give a heads up as to where you're going. Okay, so that's the intention projection part. There's a lot of work already in these areas, but we have added to that corpus to some extent, especially in using the augmented reality devices to actually provide ways of getting intent recognition as well as intention projection. So I'll give you an examples quickly. So in terms of intention recognition, you can use even very simple, course level brain-computer interfaces such as an emotive helmet to get a sense of, for example, what the humans in the loop are looking for. So in this particular task, essentially there is the robot and the human together are trying to, the human is an action observer. And you notice that there's a guy who is very happy there because he was essentially saying that I want to keep this particular green block to myself, and that can be sensed without any explicit dialogue, and the robot can then actually make its plan without taking away that particular resource. Now you might say, why don't you just talk? In fact, talking is possible. That's, of course, one obvious way we communicate, but these additional types of interfaces are also possible, and we can use that to sense the mental state. Those of you who have kept track of this neural link that Elon Musk is pouring his money into, this is supposed to be this long-term place where you can actually completely have access to human brain state. I don't know whether I want to live in that level of intrusiveness, but certainly things like even simple coarse interfaces are actually able to get you a sense of the state of the world, the brain state of the human. The other one, of course, is intention projection, where either the robot should basically make announcements saying, this is the task I'm going to do next, or essentially allow the human, and then so that the humans can then say that, okay, don't do that, do this other task. Okay, so that you actually have a dialogue. And so we actually looked at that in the context of HoloLens, where the HoloLens will basically project both the human is both seeing the real world as well as this augmented world that the robot is projecting onto the screen. And these can be used, for example, in a paper in IROS 2018, this last year, we used this to, for example, provide projection-aware plan execution. On that C there was a green dot. For example, that is the robot saying, I'm going to use that particular block. That reduces the uncertainty as to which particular tower the robot is about to construct, because upfront it could have constructed many different words, and by showing which particular block it was going to use, it can reduce the uncertainty about where it's going. So it makes itself more legible to the human in the loop. And similarly, during the execution, you can help the humans essentially provide directions. For example, the user can, by actually projecting where you are going in your, the robot projecting where it's going using those dots and so on. And since this is a HoloLens interface, actually the humans can essentially do pinching operations and so on and use that to give feedback saying, no, don't use that block, use this other block. And that is a way essentially you can have interactive execution and assistive cues. So this is sort of something that the students did, and they went last year, 2 years back actually, to Microsoft national competition and Imagine Cup finals. But now the second part, for which actually I'll spend a lot more time on, is this idea of teaming requires modeling the human's model of you, which is basically using that you will actually provide comprehensible behavior. So I mentioned that already, and in particular, when the human has a different understanding of the human AI agent's capabilities, then when a robot does a particular behavior, that might not be what the human would expect based on their understanding of the robot's capabilities. So then the behavior will be inexplicable. So that would kind of cause confusion. At that point of time, there are two possible things that the robots can do to improve, or robots or the AI agents can do to improve the collaboration. One is explicable planning. So do what people expect you to do, rather than what is actually cheaper, more optimal for you, okay? The other one is provide explanations where you get the human's model of your capabilities to the right place so that they will see that your behavior is actually optimal with respect to this changed model. And the first one essentially doesn't require any communication. In some sense, if you just do what people expect you to do, then you never have to explain to them what you're doing, because that's what they expect you to do. And the second one does require communication, because you are essentially providing a dialogue or an explanation as to how their model should be changed. And so the explanation here becomes model deltas. So how to change the human's model of your capabilities, in what direction should it be changed, so that the behavior you are showing is actually explicable to them, okay? So we use, when I talk about models, in our case, we use action, effect, precondition models for both the human and the robot actions. And so in this sort of model, essentially the differences between, so in this particular example, it so happens that the fetch robot has this funny situation where when it needs to move, if its hand is extended, then it will tip over because the center of gravity falls outside its base. And so when it needs to move, it does this rather contorted operation, which involves essentially getting its hand put under its belly before moving. And so that can be actually explained in terms of the and so that can be confusing to the humans who first see this kind of a behavior, and that can be explained in terms of these model differences that can be communicated. So in terms of explicability, which I said, where you essentially do the behavior that is optimal with respect not to your model, but rather with respect to the human's model. So this changes the optimization metric for the plan from get a plan that is optimal in the robot's model to get a plan that is executable in the robot's model and is as close to the optimal plan in the human's model as possible. Okay, so it changes the optimization metric. And so this actually, in ICRA 2 years back, we talked about how these kinds of explicable plans can be automatically generated by taking into account these distances, these expected distances from the human models. So give an example of that. Here is a scenario. This actually is a scenario, kind of scenario where, in fact, Upfront, both the human and the robot have the same model of the environment. This is sort of a simulated search and rescue kind of a scenario set up in our department corridors. And so the model of the corridors is same for both the human and the robot upfront. And then, of course, during the execution, the robot might actually see that certain paths are actually closed because of debris and so on, and that might make its model be divergent from the human's model. And using that change, essentially, basically at that point, the question is, what does the robot do? Does it do the plan that is optimal to it versus the plan that is closer to the human's model? So in this particular example, if the video works here, yeah. So what happened is that a particular path that would wind up being the shortest path for the goal is blocked. And in this case, if you go to a different path, then that would be not short with respect to the human's model. So you have one of two options. One is change the environment, basically get rid of the obstacles so that you can still go through this particular path. That's what happens in the explicable case. And the other one would be doing what is optimal for you, which will get you to the explanations part. In the case of generating explicable plans, then, as I mentioned, you have two different pieces of the optimization. One is in terms of the cost of the plan for the robot, and the other is distance between the plan that the robot has and what the human would expect. And if in this example that we had, actually the start models are known, and so in fact these distances are actually computable. In the cases where the robot doesn't have access to the human expectation model, then you need to have a learning of, you need to have a offline learning of what humans' expectations of the robot's capabilities are. We have looked at this problem and looked at a way of essentially viewing these distances, approximating these distances as essentially sort of a labeling process where a human looks at a plan and says, this makes sense, by labeling it, saying these actions make sense with respect to the goal. And then, so this labeling, learning this labeling process and then using that labeling during the plan generation such that the plans that are generated are actually going to be comprehensible to that. So that's that sort of particular labeling can be done. And in the work that we did, we used CRFs, but you could use other sequential models such as LSTMs. And so that's the way you can actually use that labeling to generate plans that are more explicable. One of the things that should be mentioned here is that in the context of learning, areas like automated planning essentially looked at fully causal models because humans have written the models of the domains. The models that you learn from data tend to be correlational models, and one of the interesting questions would be how to get by with the models that are partially causal or partially correlational models. And so we actually have been looking at learning a spectrum of domain models, in particular including things like using things like, let's say, word vector approaches to learn the action affinities in plans. So in fact, you can think of plans that have been done in the past in the plan traces as sentences in the action vocabulary and use this to kind of figure out what the action affinities are and use that to sort of figure out whether or not a particular sequence what are the best ways to complete it and whether or not it's likely. And it turns out actually that those kinds of correlational models are actually cheaper to learn from less amount of data. Of course, there is no causal information there. And we have shown that under certain cases, actually, given the same amount of data, learning fully action effect models turns out to be less efficient than learning these sorts of correlational models and using them in plan recognition tasks. So the second part that I want to mention is explanations, which basically, in this case, in our example, the robot decides, I'm not going to remove the obstacle, I'm just going to do the path that is the best path for me, and then I basically announce saying the path P1 to P8 is no longer clear. So that is the sort of general announcement. You're saying, this is the reason I'm doing this other plan. And this announcement winds up being a delta to the model. You're changing the model in certain ways such that it's now in the new, once you make this announcement to the human, if they're paying attention, they essentially change their expectation of your model. And then in that sense there, your behavior will be again explicable. So explanations as model reconciliation is this idea where we are basically saying, explainable AI is of course pretty big hot topic, but mostly as a debugging tool for inscrutable representations, such as pointing explanations saying, why do you see this is a Siberian husky? Oh, because this is snow on the ground, that sort of a thing. But really explanations are critical for collaboration beyond just debugging of inscrutable representations. And model reconciliation view, we consider explanations as essentially model reconciliations, are these deltas on models. And this actually views closer to the psychological theories, for example, of the work of Tanya Lambrazo and co. It turns out that within our approaches, we can talk about different kinds of explanations, and generating these explanations winds up basically, and these different types of explanations in terms of both in terms of length and in terms of whether or not the explanations will change over time, while other changes occur during the task, are going to wind up providing different types of properties of these explanations. From a under the hood point of view, generating of these explanations winds up being a search in the space of models. So the robot has a model, the human has a model of its robot's capabilities. The robot is actually simulating what should be the model that the human should be at, such that its behavior would make sense, and take that particular delta and provide that as an explanation. So that's essentially, it turns out that that search can essentially be made, it's a pretty hard search, but it can be made more efficient by taking some of the structure of the model, the search space. One other thing, of course, is explicability and explanations are not completely distinct from each other. It turns out that one thing you can do is, rather than just do what people expect you to do, you can get their model to change partway and then be explicable with respect to that. So essentially, you provide some announcements to essentially get their model to change some of their misconceptions of your capabilities. And then within that model, you wind up doing the explicable behavior. So you can actually combine this, and there's a paper in AMAS this year talking about how to combine this explicability and explanation within the same framework. Then so essentially, it turns out that there is an even better approach that we currently have on archive that's under review somewhere, which says that explicability and explanation can be combined by expanding the notion of actions the robot has to include explanation actions. So in addition to physical actions that the robot can do, it can make announcements whose only effect is epistemic, that winds up changing the knowledge state of the human in the loop. And then if you combine these knowledge actions as well as the physical actions, then you have a single search space within which you can provide both explicability and explanation. And so this is sort of a nice unifying way. Within this sort of a framework, actually, there's a whole cottage industry of interesting problems that you can start looking at, some of which I will quickly mention. So for example, you can provide handling multiple human agents or even a single human agent with incomplete action models. So if you have incomplete knowledge about the human agent, which is one way you would know, you basically can model the fact that you don't have the approximation of the human's model up front, that can be handled as essentially an uncertain model or multiple potential models that can be consistent. And then you can essentially reason with all of them. And then I'll show you in a minute how to do that. And you can also look at dealing with models that are at different levels of abstraction. So the first one is in ICAPS 2018, the other one is in 2018 ICHCAI. And then, as I mentioned earlier, you can also plan to project your intentions during the planning so that people increase their ability to understand what you're doing. So in terms of differing levels of abstraction, essentially, within it sort of reduces the number of models that the human can potentially have of your capabilities. So there's an abstraction lattice, and you can essentially do your search through this abstraction lattice. And details I don't have the time to go through, but that allows you to provide the support for these abstractions. And so in this case, by the way, this is also, we talk about this notion of foils, which is essentially that when you provide a behavior, the human can say, why aren't you doing this other thing? That's the way they require an explanation. And then the foil can be handled by the robot by essentially the very fact that the human asked that question localizes their place in this abstraction hierarchy, and then you can use that to figure out what their model is likely to be, and then use that to provide the explanations. Incomplete model, if you have an incomplete model, for example, with one with possible preconditions and effects, that a single possible precondition and effect will wind up being consistent with multiple number of concrete models, and you can use that to essentially deal with most relaxed and the most constrained model in this lattice. And then for those of you from the planning background, you can actually provide conformant explanations, an explanation that will work for you, given the set of models that you might potentially have. So that's a whole set of topics there like that. But the other thing is, when you come up with these kinds of explanations for humans in the loop, how do you know that it's working? How do you know that the humans are happy with what you're doing? So clearly we can just say, we made this, we have an algorithm, and it takes 15 minutes of CPU time. That's pretty good. But obviously you need to have actual studies with the humans, and engineers trying to figure out how to set up human studies is a questionable enterprise. And so, in fact, we actually work with Nancy Cook, who is a human factors expert. I'm very happy to see that there's a tutorial today, I believe, on connections with human factors and AI. That's kind of, again, very nice. That's the direction we should be interested in. If we want to say AI and human systems will work together, we need to understand how to do this human factor stuff. So, for example, we have shown in a work that's showing up in Human-Robot Interaction 2019 that the kind of explanations that our systems generate essentially are the kinds of ones that humans seem to generate in human-human Wizard of Oz studies in the same kinds of collaborative scenarios. So to that extent, in fact, the kinds of explanations we are generating do seem to be on the right action. And the other thing that we have shown in these studies is essentially that the number of times humans ask for explanations seems to be lesser if you are showing explicable behavior. So those are the two things that we want to show. Towards the ending of the talk, so implications of this sort of human-AI interaction essentially have significant implications for trust in autonomy. Everybody is very worried about how do humans and AI systems, how do humans trust AI systems, especially when they are interacting with them. So the question, of course, is one holy grail is to engender trust in the humans, but the mechanism of long-term trust are quite complex. However, of course, explicability and explanations are the first steps. If you start doing inexplicable things, people are likely to distrust you more. So at least, trust is a longitudinal thing, but certainly explicability and explanation work towards that. The other thing is, I started the talk by saying there's all these worries about AI taking over the world. AI doesn't have to take over the world by shooting people. That's the stuff that people without brains do, which is basically using guns. I always find that pickpocketing requires a lot more brains than holding up somebody with a gun. That doesn't require much of a brain. You just have the gun. So the question is, when a system can model your mental state, that allows you to manipulate you. So, evolutionarily, our ability to manipulate model our mental states helped us both to cooperate and compete with each other. And so the question then is, this raises a whole entire set of ethical quandaries about how should AI systems be interacting with humans when they are doing this mental modeling. In a paper that's coming out in IIII 19, we show that actually it's extremely easy to either cooperate or obfuscate your behavior. Explicability is to make behavior that is understandable to the human in the loop. You can also obfuscate it such that people think you're going towards one way, but you're actually going to a different goal. And it turns out it's a very small change in terms of the agent's algorithms. And the question then becomes, how do you use this ability, this newfound ability? There's a paper that's coming in AIES, AI Ethics and Society, that IIII and ACM have started last year onwards. This year we have a paper called When Can AI Bots Lie, where we basically look at human studies trying to figure out under what conditions are humans okay with being told white lies by AI agents. This is an academic exercise at this point, and when we put this up on arXiv, of course, somebody wrote an article saying, should AI bots lie? Where, of course, there is a big thing about think Skynet. So this is, again, the ending of the world. To conclude, actually, human-aware AI brings a slew of additional challenges. Much of what I did in the last hour is to try to say, A, why we should do it, and B, even for the simple case of doing collaborative interaction with humans, there's a variety of challenges in terms of learning the models and using the models. Both the learning and inference problems wind up being very hard. So why bother doing it? And I kind of remember this Kurt Vonnegut's quote that if only it weren't for the people, the goddamn people, the world would be an easier place for engineers. But, some of our best friends are humans. And we should essentially think of generating AI systems that will get along with these fuzzy humans in the loop. And as a researcher, actually, it provides very interesting set of problems that actually are open problems that I have to deal with to handle the human's presence. So that's a summary of what I have talked about. And if we do run out of time, you can always send me questions by email or tweet me. And that's a set of my colleagues that I have worked with. There is a course on the human-aware AI challenges that I have just run this last year, and that's a set of readings on that. And then I will leave at this summary and then stop. Thank you for your patience. Okay.
Thank you, Professor Kambhampati. Are there any questions? We have time for maybe one or two.
Please go ahead.
So I have two questions. One a little bit provocative. That what is the problem if somebody learns Sudoku from million instances? What is the problem? So people can learn in various different ways. So somebody is learning Sudoku by seeing million instances.
So you're saying, what is the problem?
Yeah.
There is no problem. So as far the real problem would come in terms of explaining why you made an so we share models. The reason we are able to collaborate is we share models of problem knowledge. If your systems are going to live on Mars and never have to talk to humans and don't care about efficiency, it's completely fine learning the hard way, everything by yourself. So in fact, why do we even have textbooks that some other bozos wrote? What's the problem in us learning everything ourselves by essentially, observing the world and exploring? Part of it is efficiency, part of it is also communication. So I'm not saying that you should not do it, it's that it's at least in the foreseeable future, we need this interplay of learning from the data as well as taking models that people are providing.
So this is more
Okay,
cultural.
one last question. We are short of time, so just one last question.
Yes. Actually, can you please comment on human-aware AI in a couple of application settings, like warehouse automation, which is very useful in online shopping context. Second is something like automated cars, automated driving.
Yeah, so I think, of course, automated driving, that's an actual great example. So the original Tesla autopilot is a great case in point of how not to do human-aware AI systems. Okay. In fact, those of you who are old enough might even remember Microsoft Clippy. How many of you remember the Microsoft Clippy that came? And Microsoft Clippy was this human-aware AI system that was trying to help humans. And when Bill Gates announced that Clippy is being retired, there was spontaneous applause. If there is a spontaneous applause when you retire, that means you haven't been a good guy. People are sick of you. Partly because in that particular case, the human factors things were not taken into account. So for example, in the case of Tesla, the idea is you can be completely, the system is completely on its own, but you should always pay attention to what's going on. That's impossible for humans to do. Yeah. So that you cannot come back from 0 to full attention in milliseconds. Ask the guy who went under that white truck in Florida when he was playing on the iPad. So these are issues that people are taking into account right now after making errors upfront. And then, of course, human-aware AI is also, these kinds of systems are also used in the disaster rescue scenarios where humans and robots will collaborate to save people's lives and so on. But currently, most of these are done in hard-coded fashion. In some of these, the reason we are able to write these papers is because these research problems were not actually handled before. So we currently have these systems being done hard-coded way.
Okay,
Hello, Professor.
so thank you very much. Actually, sorry we are really short of time. So I think you can, he will be around this, I think, until the evening maybe? So you can try to catch him during lunch. So I would now request Lipika to hand over a token of appreciation for Professor.
Thank you very much. I think just come here now. Thank you.
Laptop is being set up, let me introduce you all to the next invited talk by Vikas, Raykar. And this talk has a very interesting title, which is AI for Fashion. So Vikas works at IBM Research India. He's an expert in machine learning, and he's currently focused on building machines that can understand natural language and images in par with humans. He finished his doctoral studies in computer science from University of Maryland, College Park. He's also defining a roadmap for what can be done for the fashion industry, and we'll hear more on that in this talk. And he's primarily leveraging deep image and text understanding together with other AI capabilities. Okay, so over to Vikas, and I hope this gets sorted quickly.
Okay, can you hear me? Okay, so my name is, I think I'll get started. My name is Vikas, so I'm a researcher in IBM Research Bangalore. So for the past 2 years, I lead a project called AI for Fashion. Sort of fashion has been a little bit of an accident for me. I think I came from the domain of medical imaging, where we used to look at these digital mammograms and look at these small dots, which were called as microcalcifications, and then try to predict what is the malignancy or how malignant is the tumor based on this small dot, right? So for the past 2 years, I moved to something more profound, which is fashion, and I looked into something like what are the polka dots and try to predict whether will it sell more or not. So the kind of the tools I'm using are the same, but we kind of shifted domains, kind of again broader AI-based tools, moving from kind of medical imaging to fashion, yeah? So the project essentially is a much broader project talking into various aspects of fashion, but I'm going to a little bit focus today on something on the work we are doing on trend analysis and trend forecasting based on data, yeah? And that's why the title, Data is the New Black, kind of use data-driven methods to kind of understand fashion trends, yeah? So with that, I'll start off with this kind of slide, kind of also wishing you a Happy New Year for 2019. And 2019 was when, this is a company called Pantone, which is kind of almost like a color authority company, right? So this is a company which kind of defines a color vocabulary for fashion designer. And in 2019, they defined this color called as living coral as the color of the year 2019, right? So, essentially, how do you come up with a color like 2019 living coral as a color? And for example, these are the products, they kind of show you how this color kind of goes around, yeah? And they kind of sort of start announcing, and they have been doing this for the past few years, from the past 10 decades. For every year, they come up with what we call as the color of the year, right, from 2010 to 2018, and each one has a very esoteric name, which probably does not even define what the color means, yeah? So that's one example of a company. This is Pantone, which is kind of a color forecasting company, yeah? And then there's some other companies, I don't know if you've heard of this company called the WGSN, which is another trend forecasting company, which essentially, what they do is that they hire this bunch of fashion kind of influencers or fashion experts. They send them to runway shows, they go and sit there in the runway shows, and they kind of come back, sit in a room and find a kind of very kind of a subjective opinion of, okay, what is trending there out in the world of fashion, right? So again, and then what you do is that every month they get you sort of a PDF, sort of a report on what they think is the current fashion trends. And again, every fashion house there in the world, every retailer subscribes to WGSN reports. They charge to the order of around 5 to 10K per month subscription report. And in a way, I gave you these two examples, which is Pantone and WGSN. So these are both kind of trend forecasting companies, but they are heavily expert-driven companies, right? So essentially, they have a lot of people who work for them. They are the subject to experts who sit in the companies and come back, sit in a room, write reports, and then kind of decide, okay, this is the trend for the next season. And the big criticism for these kind of companies is, in a sort of way, they define the trend, sort of, right? So you have the authority and you're the world leader, you can just get to say what you want to be the color of the year and everyone has to follow, that should be the color of the year, right? So essentially, this has been the motivation for some of the work, what we do, what we call as the Fashion Zeitgeist project, essentially to say, can we take a more data-driven approach to the same problem, right? If I give you a bunch of images, if I read you a bunch of articles around there, can you tell me what is trending there out in the world of fashion, right? And we're going to try to formalize this, make this notion more crisper, yeah? And this is really more important in fashion because while fashion is a very highly creative business, eventually it has to sell. And it's probably one of the hardest business because typically the cycles have been like 6 months to 1 year, right? So you start designing now with the hope that what you design now will sell 6 months or 1 year down the line. At this point, which essentially everything can change, and fashion trends move so fast, you're essentially making a guess on what will sell next 6 months in the down the line, right? So typically there is this big kind of onus on a designer to be very aware of fashion trends so that not just aware of what is currently trending, but he has to essentially hedge his bets that what I'm going to design now and going to spend a lot of money to kind of manufacturing it has to sell 6 months down in the line because the whole supply chain from this design conception to back into your store takes around 6 months traditionally, yeah? But this has been changing now with the emergence of fast fashion retail like Zara, Uniqlo, H&M, where they kind of essentially trying to do a much leaner, agile supply chain where you see now and probably within 3 to 4 weeks, Zara can bring it back on your stores, right? So, but that kind of needs your complete supply chain to be designed. But traditionally, a lot of fashion retailers still there is a 6 months kind of delay, yeah? So that's why kind of the whole problem of essentially kind of understanding fashion trends, and there are two parts to it, what I call as trend analysis and trend forecast. Trend analysis is essentially figure out what is the world is wearing right now, right? And there's a lot of data out there. Can you just get a feel for what is going on? I mean, essentially that's what designers do, right? They go to fashion shows, runway shows, they look around, and they get a feel for the fashion zeitgeist. But if you have a collection of images, how do you do that? The second is the forecast part. Based on that, can you try to guess what's going to happen, say 6 months down the line? I mean, I understand fashion is irrational, but we can anyway guess what's going to happen, right? So, and the reason also why it also has a little bit more deeper kind of impact is because, so almost every fashion retailer has a big inventory problem, right? So if I talk to many fashion retailers and everyone, if you look at, say, if they produce around 1,000 SKUs per season, roughly the number I've heard is around 60 to 70% sell well and 40% really does not sell well. It's roughly as good as a coin toss, right? You're just randomly guessing what is going to sell and not going to well. And for example, traditional lot of Indian retailers, they have a lot of the second-hand shops where this move goes, but very kind of brand-conscious brands like, say, H&M, Burberry, wherever, they have this huge inventory of every season, they have this billions of dollars of unsold inventory. And what, I mean, for example, H&M, I didn't put that other blurb was kind of in controversial news last year because they ended up burning this around $4 billion of clothes, right? They found it out cheaper to actually ship it to a coal mine to use it as fuel rather than kind of repurpose the clothes, right? So there's essentially every kind of retailer, even Burberry was accused of kind of destroying inventory does not sell. And that's why it's very crucial to be kind of and that's the space we're trying to operate it. So trends is one aspect of it, but overall, how do you make sure that there's no excess inventory for a fashion design house? And it does not, the one way what you're going to talk about is right at the point of conception, right? When the actual design starts, what can you do about it, yeah? So this is a broader project, what I said for the AI for the fashion project, where actually we're trying to build some kind of, lot of AI-based tools. I mean, you can take as visual search, fashion annotators, image understanding, text understanding. The only thing is that we kind of take the generic purpose AI tools, but we collect a massive amount of fashion-related data and create these pre-trained models which work well on the fashion domain, yeah? So that's essentially the whole project is about. And so what we're going to focus a little bit on today is about what is called as a fashion, using such kind of tools to understand fashion trends, right? So we'll start off with the question of so this essentially started out simple question from a designer saying, can you predict what are the trending colors, right? So, and everyone has this notion of what is a trend kind of a little bit vague in their heads. So we try to explain what does actually a trend mean, right? So a fashion trend, if something, let's say there's a trend for animal prints. So it can arise in multiple kind of places, right? That some designers have started showing fashion runways animal prints in runway shows. Maybe celebrities have started spotting it. A lot of e-commerce sites are actually showing animal prints on their sites, and they're selling out faster, and that's also an indication of this. And sometimes it could even be that some guy posted on Instagram some picture of animal prints, and suddenly it got viral and it caught on, right? So a trend can arise from multiple sources, but the general notion is that a trend is something in which there is a general direction, or typically upward, in which something is developing or moving, right? So a trend does not mean very popular, but there is this notion of time that there's something which is changing and which is changing very fast, yeah? That's what we want to try to capture. So we're going to, just to make things more concrete, I'm going to look at this small example of a data set which we started. So we're going to look at all the runway images from 2013 to 2017, right? So this typically, there are totally major 4, London, Milan, Paris, New York, there are major 4 runway shows, but there are other smaller subsidiaries. And every year, there are 2 seasons, autumn, winter, and spring, summer. And every year, designers come and show their collections there, right? And that's where the kind of, you can think of this whole trickle down in fashion. That's where the whole kind of sort of the trends get defined, and then it essentially trickles down to the mass market slowly, right? So we're going to start looking at this data, and this is also timestamp data we have from 2013 to 2017. Can you just check this? It's not moving. Okay. So one of the kind of, if you look at a typical runway show, essentially you will get around close to 100,000 of images. And the whole kind of value prop we have is that no designer sitting in one room or no kind of fashion observer can actually get a feel for what is going on in the fashion by looking at all the images. And that's where some of these data-driven models help, yeah? So essentially, to make it more concrete, we break down into 3 parts. One we call as the color, print, and the silhouette. And today I'm going to mainly talk about kind of the color trend analysis and forecasting. And then we'll later see about, if this time permits, go into print and silhouette, yeah? So first is about colors, right? So essentially the pipeline starts like this, right? So first you have to take a fashion runway image, but typically you have to have a good person detector, right? The biggest problem comes in a lot of this method is essentially we need to focus on the person or the apparel, right? There's a lot of background thing, and we need to ignore all the background. And there are a lot of these models where we try to focus on the background, and then we try to estimate the pose of the person. Based on that, essentially we have a lot of these annotators which can take this image and break it down into different apparel, right? So currently we work with typical YOLO style bounding box algorithms, but you can essentially think of having more precise mask semantic segmentation algorithms which can get you the actual precise apparel thing, right? So once I know actually which region to focus on, I need to find out, I'm going to find out, given this certain particular region in the image, can you find me what are the dominant colors in that particular image, yeah? So one way to do it is essentially kind of, I can train a machine learning model and try me whether it's color, orange, etc., right? But there are much simpler methods what we can do. So typically we look at, a color is defined by 3 numbers, right? R, G, and B, right? So, but if you look at, you take an Adobe tool and inspect every pixel in this RGB image, you'll find millions of different shades of RGB, right? So you'd never know what is that particular orange shade. So that is typically what you do is you would look at all the pixels, apply some clustering algorithms. You would not do it in RGB space because RGB is not a perceptual space. You would do in something called a lab space. You do some clustering and try to define that these are the dominant colors in this image, right? And you would say that, okay, I want to pick up K dominant colors. So give me the 5 dominant colors, right? And essentially you can, given any image, you can get what are the fraction of the pixels that are assigned to that particular dominant color, right? And while, the clustering algorithm is good, I think it's a little bit unstable because every time you initialize, you get a different color, but there is actually a much more simpler method called as modified mean cut quantization algorithm, which was actually proposed back in the times of this displays where there were video games where you could not actually render multiple colors. So the problem was that given any image, and if I have to render it with only 5 colors, what are the 5 colors you would pick, right? And that's essentially your quantization algorithms. And that's much, much faster and works very stable, right? And those algorithms we use and to kind of get you the precise RGB value, so saying that this is the dominant color in the image, right? So that's the first part. So the second part is a little bit more tricky part, right? So now that I have an RGB value, I need to associate a color name to it, right? RGB is what, 3, right? There are 255 values, so typically they're all possible colors are what, 256 to the 255 into 255 into 255. There are probably millions of colors, right? And color vocabulary is completely messed up, right? So essentially, as I may know, probably around 10 colors, right? Which is essentially the primary colors, red, blue, green. But But maybe someone which is more color literate can probably reel out around, say, 100 colors. But if you look at Pantone, which essentially defines a set of around 2,300 color names, right? So, and the colors can be very esoteric, something like, they may even call something like, the color is serenity, right? I don't know what color that evolves in your mind, but serenity is a color. Ecru is a color, right? Which is, do you know what ecru is? Ecru is something which is very closer to orange, right? So the associations between an RGB value and the color names, again, itself is a big research problem in itself, believe me, right? So just to get to how to get a color name out of an RGB value, right? So, and so, I mean, the simplest thing you would probably take is that you would, essentially what we do is that we build these color taxonomies. We go to the web and crawl every possible color name and get their color names and the RGB values. And then given a particular RGB, try to find what is the closest one, right? I mean, I would actually probably believe that I can just take the Euclidean distance of the RGB value to two colors and find what is the similest color. But it does not work that way because it seems RGB is not a perceptual space. I mean, there has been, again, this itself is in a tons of research has been done on how do you define perceptual similarity between two colors, right? I mean, forget deep learning, just given these three numbers, RGB values, and just another RGB value for second color, can you come up with a metric which tells you how similar two colors are, right? And similarity as defined as how people visually perceive colors to be similar, right? Things should be similar, that should become, right? So, and then there are this very specialized metrics, something called the delta CIE 2000 metric, which has been done in the color literature where it tries how two similar colors are together, yeah? So eventually, I think, so that's the word, right? So I get an image, I can find out where the apparel is, then I can get you the dominant RGB value, and then I can have a module to map this RGB value to the corresponding Pantone color name, yeah? And then we can, there are certain other, I'll skip this, there's something called a color search. Now we can do, given a particular color, find which images are there. And this is what I was saying that these are all according, I mean, these are, I mean, do you see any differences? I mean, these are actually all different unique colors in the Pantone, right? Each one has a different unique name. So that's the thing in fashion, that I can't just go and say that blue is the next color, right? I mean, that's like what's, I mean, there are only 7 colors. You can't just tell blue or purple is a color. I need to get you the precise particular shade of RGB value, that kind of work. And that's why we need to be very nuanced in terms of describing, getting the particular RGB shade and then getting the names, yeah? So essentially, so, okay, so till now where we are is that I can get you an image and I can get you essentially what are the dominant colors for the apparel that the person is wearing in the image, right? So now we are moving to one step further. So if I give you a collection of images, let's say everyone in this room, right? And I can get you what are the colors, what are the most dominant colors around that in this room, right? And that's essentially what would be the next step of analysis we would do is move from one image to a collection of images. And the collection could be anything, right? Think of collection could be all the images in 2013 which came out in spring, summer, or it could be autumn, winter 2000 collection room, right? And so I can actually look at the room and tell me what is the most popular color, right? And that's essentially one way of solving this problem, tell me what are the most popular colors for this particular season, right? And again, so we can analyze colors either in two ways, right? That's where it gets a little bit technically challenging. One is what I call as, you can analyze either in a discrete space, right? Where I given an image, I can tell you that this is blue, this is red, this is color. I can get you a particular textual description of it. Or I can either do in a continuous space, which is the actual RGB value, right? Which is again a 3-dimensional space, yeah? So if I do it in the discrete space, essentially it is counting. I look in the room, I see how many people are wearing black and declare black is the most dominant color or the popular color for today, yeah? Or if I look at the continuous space, I essentially go to each of you, extract your dominant RGB value, and then do a clustering algorithm and pick up a particular RGB and call this RGB shade as the dominant color for today or the popular color for today, and then associate a color name later, yeah? And reason I think kind of in fashion, what we are trying to move towards is what I'm trying to do is analyzing trends in continuous spaces, because fashion is highly visual, right? Something which is, so that typically what happens that the vocabulary for a particular look or a particular pattern typically comes much later than the visual image. I mean, for example, I don't know how to describe your print, right? For example, the top, it would probably a botanical print or whatever, but typically it's an image, right? It's, for example, something is checks. These are very common things, but new patterns, new silhouettes, new colors emerge, and for which, frankly, there is not even a vocabulary for it. There is no term for it, right? And that's why you cannot actually rely on textual methods where you can actually first build a pipeline to extract that particular attribute and then track the trend for that attribute, right? So what I'm trying to say is that we need to actually look into the original image itself. color is one simpler example, right? You can just track trends in the particular RGB space, but it could be some embedding space for a print, or it could be some FC6 dimension of, let's say, a silhouette, and try to predict. So rather than saying that this is the dominant silhouette, that bell bottoms are the dominant silhouette, I would say that this FC6 is the dominant silhouette for this season, and then you make out what it means. Yeah. So that's essentially the second step, right? So I essentially go from this, and then I get into the dominant colors. Yeah. So that's how I think we can essentially get to what is the dominant color palette for spring, summer 2017, spring, summer 2016. So I can essentially start producing these palettes just like WGSN or Pantone does, right? But it's in a pure data-driven way where I don't really care about what is this experts are saying, yeah? So now I want to move to one step further. So I'm going to ask the question, and we started with this exercise, right? So what I did is that I took a bunch of images, I extracted the colors and did some clustering and said, okay, these are the dominant colors for this, right? But is trending same as popular, right? So when I mean as popular means that I just look into the room and I say everyone is probably wearing black or blue, I would say that black and blue is the popular color, right? But that's not the most interesting thing because I can just look out in the room and guess what is popular, right? And what fashion designers are actually interested in something called as trending colors is something which is, and there's a time aspect to it, something which is not popular yet, right? For example, I come to this room, yesterday I saw, okay, there was a couple of people who are wearing, let's say, orange, or let's say coral, orange color, yeah? Today I came to the room, I saw like, okay, there are more people wearing orange. And tomorrow I come, there is a sudden big mass of people wearing orange, right? So there is a sudden sharp uptake in kind of people in oranginess or whatever you take, right? And that's what we want to define as a trending color, right? Where it's not just what is popular, but essentially one which is kind of, there is slow, sharp uptake in popularity over the past few, let's say, in days or months or whatever, right? And technically, it's essentially the ones which have the highest slope in this trend graph, yeah? So this is just to give an example, for example, so once we have this collection of images and we have time-stamped images, right? So here I know I have a collection for 2013, 14, 15, 16, 17, etc. And I can actually see what is the popularity of particular that RGB shade. And then I can actually start looking at tracking the popularity as a function of time, right? And then try to kind of see the ones which have the highest slope in this trend graph are the ones which are the trending colors, rather than the ones which are the most popular colors, right? If you do sort of, and then again, so then we can actually do our favorite regression model, time series models, and do forecasting, right? You just take for each color, you have your popularity function as a function of time, you try to regress it for the next year, and then try to predict, okay, and you do this for every possible colors, and then you could say probably this would be the next trend for interesting colors for the next season, right? So forecasting is a natural kind of step from analysis, kind of we just are fitting a time series regression model to the next step, yeah? So I think I described you a very kind of a little bit intuitive way, but you can do there are more formal ways of doing it. Essentially what I've done is essentially doing clustering and tracking the cluster strength. But a more formal way would be you could do a spatio-temporal Gaussian mixture model with a time-varying coefficients, and then you track how the time-varying coefficient would change. Or you could do a spatial-temporal kernel density estimation, and the trending colors would essentially be the tracking the modes of the derivative of the density, which would be the most interesting things, right? So I just explained you this concept, but the same thing now you can think, you can extrapolate rather from this three-dimensional space of RGB, take it to prints, take it to silhouettes, right? You are essentially tracking something in, there's a time thing, spatio-temporal thing, and then you're tracking the modes of this and trying to things which are the modes are the most trending aspects, yeah? So I think once you do these trends, I think that's when the most interesting colors come up, yeah? I think since I have just 5 minutes, I'll just briefly end with a small case study, what we did with a designer. So this is we started collaborating, I think this is a couple of years back with a designer called Jason Grech, where again, so he said that, okay, I want to use some of these AI tools in my design process. And typically what happens is he spent a lot, the way they work is he spends around 2 to 3 months kind of building this mood board for the next collection. And the requirements are pretty vague, kind of, I want to do something, like I want to do something interesting, right? So what we did was we thought we'll do you the color research for you, right? So essentially we said, okay, give me your source of inspiration, what are the hashtags you follow, what are the Instagram hashtags you follow, what are the Pinterest boards you follow, which are the runway shows you would follow. So give us a big, massive collection of image banks, what you follow. And we applied these similar tools and gave him kind of a trend dashboard, kind of created him a dashboard of, sort of we created, I mean, we took over the color part from his research, right? We said, okay, we're going to create the color mood board for you. And we think these are the colors that you should focus on. And then he started picking some colors from this for his next collection, yeah? And so this is the final output, right? So essentially we started out with around close to 600,000 images, went through all this number crunching pipeline, and gave him a bunch of kind of what we think as the dominant and the trending colors. And finally he chose some colors what he liked. And eventually the color was what he used from the palette we predicted, and the rest all of the design aspect was his. And then he kind of gave thing, right? And this is what he calls them as the final collection of these 12 pieces, which essentially he debuted at the Melbourne Spring Fashion Week, I think last year. And each one is actually, each color is coming from the palette what we had predicted, right? So I'll just skip over briefly of this. And these are all some of these interesting colors that have come up, right? And so I think the one thing is that he was a little bit, he was a bit hesitant kind of initially to use this. I mean, you just give me a palette, what is it, right? And he said, okay, then he kind of apparently was just visiting the Paris couple of fashion weeks, and he actually saw sort of some of these colors being popping up here and there. And that kind of gave him a validation that, okay, I need to trust some of these. I mean, if you look at Jason Grech pre this and post this, earlier I think he was a pretty moody and his colors were very dark and kind of, I don't know, like very kind of purplish, brown, black colors. But now after post this, kind of he said that he has turned completely pastel, right? So he's a big proponent of pastel colors, and he claims that these colors are actually selling 3 times more popular than what he used to sell earlier. And this is just one kind of case study I just wanted to show you. And if you're interested, there are more other interesting collaborations, designers, what we have done, and more other interesting use cases we looked at. So you can talk to me later, yeah? Thank you.
Thanks, Vikas, for the very interesting talk. We won't have time for questions now, but he will be around, so please catch him. If you have any questions between that marriages AI with fashion. It's a very interesting area to look into. And next, I would request Lipika to give Vikas a token of appreciation from our side.
I think there are a few announcements. We'll wait for a minute or so.
You know the drill already, right? So everyone leaves the room with their staff right now, okay? We need to get the rooms ready for the next session. There's coffee and tea outside. However, I want the session chairs and the presenters for next session to be ready near their podiums. We need the presentations to be uploaded and ready in the next 20 minutes. Thank you. Everyone else, please go out with all your bags and everything, your jackets.